Now let us discuss about the series combination of a resistor and inductor and what is the value of current in that circuit. Let us consider a series combination or a series circuit of a resistor and an inductor. This represents the resistor. We call its value as R, a resistor of resistance R, and an inductor. This is the inductor of inductance L. These two are connected in series across an AC source. We know the voltage across the voltage supplied by the AC equal to V0 sine omega t, where V0 is the peak value of voltage, omega the angular frequency, and t the time at any instant. See, this voltage divides between the resistance and inductor. Let VR be the voltage across the resistor and let's say VL be the voltage across the inductor. This cannot add simply because there is a phase difference between the flow of current through the resistor and the inductor. We'll discuss it in the phasor diagram. So that let's draw a phasor diagram. In order to find the current, we need to draw the phasor diagram. Let this be the y-axis and this be the x-axis. X-axis, this one is the y-axis. Let's take the current in this direction. Let this be the current. We know for a resistive circuit, voltage for a resistance, the direction of the current and direction of the voltage are in same direction, or we always say voltage and current are in the same phase. So since I took this as the direction of current, the voltage across the resistance, which is in same phase with the R, is also in this direction. So we can call this as VR. This length is small. We considered the value of current is smaller than the magnitude of the voltage. So we take a small arrowhead for the current. Now, what about the voltage across the inductor? We know there is since this is the current across the inductor, the current in both the resistance and the inductor remains the same because they are in series combination. But the voltage is always ahead of the current by a phase of 90 pi by 2. We already discussed this in the previous derivation. In that purely inductive circuit, we already discussed there is a phase difference of pi by 2 or 90 between the current and voltage, and also the voltage leads the current. So I have to draw the voltage in here. So this represents the voltage across the inductor, and this angle is always 90. Now what we have to do is we need to find the resultant of this VL and VR. For that we have to complete the parallelogram. It's actually a rectangle since one angle is 90, and this length represents the resultant voltage. We call that as, let's say, V. Now let's name this as O, this point as A, B. This angle is also 90. Now if I take this, I draw this triangle here. This is our O, this is A, and this is B. This length is actually VR, and this length is VL, and we have angle A equal to 90. So OB is the resultant. Now how will you find the, how can you find the relation between VR and VL? We can use the Pythagoras theorem. Clearly the V square is equal to VR square plus VL square. Also we know voltage across the resistance is current into the resistance, value of resistance, and the voltage across the inductor will be current in the current times the value of inductive reactance. This is the inductance, and we have XL equal to inductive reactance, which means the resistance offered by the inductor to the flow of AC. So we can write this as V square is equal to IR whole square plus IXL whole square. Simplifying, you will get V square equal to, this can be written as I square R square plus I square XL square. So this equal to V equal to V0 sine omega t. Simplifying this, you will get V square is equal to, you can take this I square out, I square into R square plus XL square. Now taking the, if you take the square to the right side, we can write V as the root of I square times R square plus XL square. So we can write V equal to I root of R square plus, we know XL is equal to angular frequency times the inductance. So this become omega square L square, since X equal to omega L. Now taking the I to the left, you have V upon I is equal to root of R square plus omega square L square. Now we know the voltage by current, the ratio of voltage to the current is always the resistance. But here it is not the simple resistance, the combination of resistance offered by the resistance and the inductor. Or we can say Z equal to root of R square plus omega square L square. And we call this Z as impedance. 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 Impedance is nothing but the resistance offered by the combination of resistance and inductor to the flow of AC. Impedance, depending upon the circuit, the factor which gives the impedance varies. For example, if we have a capacitor here, the impedance is offered by the resistance and the capacitor. Now we can call this as this impedance as the impedance offered by the series combination of resistance and inductor. Clear? So let me write this as, we derive this. We derive the value of impedance. We have Z is equal to root of R square plus omega square L square. Now we need to write the value of current. See, we always take the voltage, the value of, the vector, the voltage, the angle made by the voltage with the x-axis as omega t. So this is omega t. And let's take this angle as phi. That is AOB. Let's call this as x. Let angle XOB equal to omega t and angle AOB is equal to phi. That is, this angle is phi. And if you take the value of tan phi is actually opposite side. Here it is AB upon the adjacent side OA. Or you can write VL divided by VR. That is, tan phi is equal to, we already discussed, VL equal to IXL by VR is equal to IR. Cancel this I and I. Again, XL is omega L by R. Implies tan phi is equal to omega L by R, or phi equal to, taking the tan to the right, it will be tan inverse omega L by R. So this is the phase angle. Okay. So phi equal to tan inverse omega L by R. Now we need to find the value of current. From the figure itself, you can see that current, this is the current. Current is always behind the voltage. Clearly, I equal to, before that we have to find the peak value of current. We have I0 is equal to peak voltage divided by impedance. Or you can write the peak voltage divided by impedance is actually R square plus omega square L square. So this is the value of peak current. And we know current I is equal to I0 sine. When you look at the value, this is the angle made by the current vector with the x-axis. Clearly, this is equal to, from these two, we have angle XOA is equal to XOB minus AOB. That is angle XOB minus angle AOB, which is equal to omega t minus phi. So this is equal to phase of current is equal to sine omega t minus phi. Clear? So this is the expression of current in a series combination of resistance and inductor when applied across an AC. Or you can write I is equal to, let me write here, I is equal to I0 sine omega t minus, instead of phi you can write this, that is, let's put a square bracket in here, tan inverse omega L by R. Clear? This is the expression for current in the series RL circuit. Clear?